second type of reaction that I want to talk about today is the redox reaction. In a redox reaction, elements transfer electrons and they change in oxidation states. Redox reactions involve two types of reactions, reduction and oxidation, hence redox. Reduction is the gain of electrons. Oxidation is the loss of electrons. The clever mnemonic you can use to remember this is EO goes GER, loses electrons oxidized, gains electrons reduced, or you can use oil rig, oxidation is loss, reduction is gain. Either of those are good and clever to remember. Let's talk a little bit about reduction. So reduction is the gain of electrons, and when you are gaining electrons, it means that your oxidation number or your oxidation state is going to become more negative. In redox, almost everything is sort of backwards. It's almost sort of counterintuitive. You would think that if you're gaining more, you have a positive, just like if you're gaining more money, your bank account increases. Well, electrons aren't like money. Electrons are negatively charged. So adding electrons is almost like adding debt. If you spend more on your credit card, your balance is going to become even further in the red. Same sort of thing with electrons because they're negatively charged. So oxidation numbers become more negative as you gain more electrons. A substance that is reduced is an oxidizing agent. That means that when something is being reduced, it's gaining electrons. This substance has to pick up the electrons that are lost by the oxidized substance. Oxidation is the loss of electrons. Oxidation number becomes more positive because you're giving up those negatively charged particles. It's like paying off a little on your credit card. Your balance is going to become more positive because you're getting rid of some of that debt. And oxidized substances are reducing agents. The reason you have these two terms is because these two reactions must happen simultaneously and in cooperation with each other. If they don't, you have loose electrons. Loose electrons are bad because they create what are called free radicals. As you know from your experience, free radicals are bad. Therefore, oxidation and reduction reactions have to occur in tandem. Okay, so here is where we're going to learn about how to assign oxidation numbers. You can find this chart attached to the solubility rules on Joule. Okay, so here are all the rules. The first rule states that the oxidation state of an element is 0, including all elemental forms of the element. In other words, whenever you see a compound and there's only one type of element in that compound, its oxidation number is 0. No matter what number is shown in that element's composition or that compound's composition, the oxidation number is always 0. O3 is ozone, and it has an oxidation number of 0. Just like O2, oxygen, also has an oxidation number of 0 because it is in elemental form. That's all number 1 is saying. Number 2 says the oxidation state of a monatomic ion is the same as its charge. Monatomic means only one atom. An example of number 2 would be something like lithium. Only one atom. Whatever the charge on that atom is your oxidation number. So lithium Li plus has a charge of +1, oxidation number also +1. In compounds, fluorine is always assigned an oxidation state of -1. Fluorine is the only compound that is never anything other than -1. Number 4 number 4, it says oxygen is usually assigned an oxidation number of -2. Now this is probably true for about 99% of all oxygen-containing compounds. The exception is when oxygen exists as this ion, or in other words, as a peroxide. The only time you would see this is H2O2, or sometimes you'll see Na2O2. Here, oxygen has an oxidation state of -1, not -2. So always be on the lookout for that. Hydrogen is almost always +1. The only difference would be if it's a metal hydride and then it has a charge of -1. That's not something that you guys will see a lot in the course of your homework or quiz or exams. The sum of the oxidation states, number 6, the sum of the oxidation states must be 0 for an electrically neutral compound. And number 7 is basically the same thing. For a polyatomic ion, the sum of the oxidation states must equal the charge of the ion. This is the same thing that we were talking about when we were talking about charges and how they must balance to equal 0. Okay, so let's practice identifying oxidation numbers. Now, shucks. I'm going to have to get you a better table for this because it doesn't include all of the things that it needs to. Okay. For anything that's not included on one of these 1 through 7 rules, look at your standard charges on your periodic table. Those standard charges will be the same as your oxidation number. So here, chlorine will have an oxidation number of -1, potassium +1. Here, barium you can find +2. And now let's talk about this SO4. SO4 is a polyatomic ion, and the SO4 has a total charge of -2. Number 7 on your rule sheet states that if you have a polyatomic ion, the sum of all of your oxidation numbers must equal this charge. Okay, so oxygen is not a peroxide here, therefore it's -2. And the way you can solve to figure out what you need to have for your other your other element is in this fashion. So you have 1 sulfur, and when you add that to -2, that's the charge on the oxygen, times 4, because there are 4 of those oxygens, that needs to add up to a total charge of -2. Okay, so let's just do a little bit of algebra here. S minus 8 minus 2 times 4 is -8 equals -2. Now we want to solve for that S, so we have to put the 8 on the other side. So to undo a subtraction, we have to add +8 to both sides. So therefore, sulfur in this case is going to be a +6. Now you can, on your polyatomic ion sheet, write these numbers down, because every time you see the sulfate ion, those elements will always have those same identical oxidation numbers. That does not change as long as your polyatomic ion is intact. Okay. Let's do another one here. Okay. In this case, we're going to calculate the oxidation number exactly the same way that we calculated charge when we were trying to name these guys. So here, we're going to have to break this apart. OH is on your polyatomic sheet. It has a charge of -1. Now, we can solve for all the different parts of the hydroxide section. we're going to have a -2 and a +1. If you do the math there, that makes sense. The O is -2. That math checks. Okay, so then if this is the case, here you have -2 and a +1. So you have a total charge here of -3. This charge here has to be a +3. The charge is the same as the oxidation number. They're virtually identical. Okay, here's an example of chromium nitrate. We can do the same thing that we did for that iron hydroxide. NO3 has a 1- charge. The oxygen is -2. The N we don't really know about, so let's solve an algebra problem for that. There's 1 nitrogen plus -2 times 3 has to all add up to -1. So N minus 6, therefore N equals +5. Now you can write these oxidation numbers down on your polyatomic sheet because those will never change as long as you always have NO3. Now, because this is a minus charge and there's 3 of them, this has to have a charge of +3. Okay, let's do an example of this concept. And the loss, how we can tell if something is losing or gaining electrons. Okay, so let's balance the equation first. That doesn't work. 3 here, and a 3 here, and that's right. Okay, so it should be 1, 3, 2, 3. Okay, so now let's go through and identify the oxidation numbers for each element in every compound in this equation. Okay. Here we have a -2. Now, here we have a case where there are 2 irons. 2 Fe plus -2 times 3 for the oxygen has to equal 0 this time. We have a compound that doesn't have a charge, therefore it's neutrally charged 0. Okay, let's do the math here. Here, iron is equal to +3. Yes, you can just switch those numbers back. I just wanted to show you the algebra. Here you have -2. In this case, the copper must be +2. Aha! What is your oxidation number here for the iron? It's in elemental form, which means it fulfills rule number 1 on your table. It's an oxidation number of 0. And then finally here we have -2. And now this carbon we don't know anything about. So we have 1 carbon plus -2 times 2 yields 0. So after our algebra, we get a result of +4. Okay, now the thing for oxidation and reduction is that you're going to have a change in oxidation numbers within your chemical reaction. Find the 2 elements that have different oxidation numbers on either side of the chemical equation. The iron is going from +3 to 0. Is that getting more positive or more negative? +3 to 0 is getting more negative. When things get more negative, that means that's the substance that's being reduced. So let's just write on here that iron is reduced. Now the other substance that's oxidation number changes is the carbon. It's going from an oxidation number of +2 to one of +4. Is that getting more positive or more negative? That's getting more positive, therefore you're losing electrons, so it's oxidized. Now, remember that whatever is reduced is the oxidizing agent. So this species here is our oxidizing agent, and here the carbon is what's oxidized, so this is our reducing agent. How come I circled carbon monoxide as opposed to carbon dioxide? Let's talk about that. Oxidizing and reducing agents must be reactants. That's why I circled the carbon monoxide, because it was on the left side of the equation as opposed to being a product. The agents are the things that are picking up or losing the electrons. Therefore, they have to be reagents. I'm going to abbreviate these things always. OA for oxidizing agent, RA for reducing agent. Okay, let's do one more example. When you add nitrogen and hydrogen, you can form ammonia. Balance this equation. And identify the oxidation numbers. You should pause it and try to do this on your own. Nitrogen is going from 0 to -3. Is that getting more positive or more negative? More negative. Which one is that? Reducing or oxidizing? Reducing. So that thing is reduced, which means it's the oxidizing agent. Hydrogen is going from a 0 to a +1 charge, which means that it is oxidized. It itself is losing the electrons, which makes it the reducing agent. This can get tricky, so if you have any questions on this, please feel free to email me right away or call if you need to discuss any of these things.